I'd like to thank especially the Blue Waters project for making all this work possible. And of course, we're so fortunate to have support from NSF over a number of years. And I've listed the names of several collaborators who have contributed to various parts of the material that I'm trying to cover, and also doing all these years, at least 4 PhD students of mine have benefited from access to Blue Waters, and of course that made their own contributions. And 2 of them actually here. One is going to be graduating in a few months. So I'd like to try to keep this slide as clean as possible. Wonder how many of you have seen it. This is a painting, it's not computer visualization. It would be very nice if some computer visualization generate exactly the same kinds of things. Those was the Italian artist Leonardo da Vinci. He lived this was some 500 years ago, and someone if you're not too familiar with turbulence, you might ask me what it is, and I can say that is it confusing. So that's what turbulence is about, and I would like to avoid having too many words on this slide. I think the preceding speaker already made my task a lot easier in introducing the importance of turbulence and also why high-performance computing can be helpful. So of course we have a disorderly fluctuation over a wide range of scales in both time and space. Turbulence is important to atmospheric scientists, planetary physicists, as pointed out in the preceding slide, and of course in many other disciplines. The Reynolds number is important, and the Reynolds number is important here as a measure of the range of scales that we have. And numerical simulation often is the best source of detailed information. Maybe some experimentalists would not perfectly agree. I'm not saying that we should not doing any kind of experiments, because frankly we do have to acknowledge that numerical simulations, while very promising, we also know that we have our own problems. And it's a great challenge problem in high-performance computing, I think, because we can get away from the fact that the fluid in the room, let's say, has perfect freedom to move in all 3 directions. So we have to decompose the domain, and it tends to be communication intensive. And also one of the challenges for turbulence people is that every time we want to step up the problem size, let's say, how about you want to double the number of grid points in each direction? That means that altogether you have an 8 times jump in the number of grid points. Very often you find that people go from one resolution to another. Well, it will take a few years, maybe a different computer very often. Some of the notable references in the field included those here on the Earth simulator, 2003. Some Japanese scientists who have come to know pretty well. They did the first ever 4096 cube simulation when nobody in the world had done 2048 cube. So that was tremendous impact. That something. And then we have tried to catch up on. Over the years on Blue Waters, we were able to publish a simulation at 8192 cube, and of course, nobody is resting at 8192 cube. And so in Japan, they have some other simulations as well. So what are some of the fundamental questions about turbulence? We are very interested in intermittency. We would basically ask, well, how large can the fluctuation ever be? Okay, so last year in August, Houston area, they have 50 inches of rain. Is that very extreme? Okay, so nobody can predict how many inches of rain we can have, we're going to get. But how extreme that is? That seems to be a fundamental question. Not easy to answer, in fact. Can somebody say, look, 50 is the maximum limit, that will never happen again, and we don't know. And in terms of Reynolds number, a lot of theories of turbulence assume, say, a sufficiently high Reynolds number, something happens. What is sufficient? We don't know. There's no clean answer to this. That's what I'm saying. And turbulence is important for mixing and dispersion. How far do things far apart come together, or maybe the other way? I think that was the preceding talk about, say, if you have 2 particle pairs, if you have 2 particles, those being a inertial particle in the previous talk. Well, what can we say about how far they're going to move apart? And also we want to know does molecular diversity matter anymore? To some extent. And turbulence, of course, is important in a very broad context, a lot of other contexts, combustion, about dynamics of the ocean. I would say that if you want to design, improve engineering devices, be able to respond to a national disaster, be able to respond to natural disasters better, we need to know something about turbulence. What has the blue waters allowed us to do over the years? And we have done force of the tropic turbulence that is relevant to the preceding talk. We have a high Reynolds number. I think based on the Taylor scale Reynolds number, we have 1,500. We've done this at various resolution. We wrote time for the for PREC grants saying that we're going to do 8192 cube. It turns out that we are not satisfied after we've done that. And how do we go a step further? Now, we have made some limited progress at too high resolution, the highest being 16K cube, which is what I mean by essentially 4 trillion. And of course, we benefited from using hundreds of millions of core hours, and as a result, produce a lot of data. Then, when the quite big question is where we're going to put them. Here, we have used the blue waters to investigate several aspects of turbulence. We have also one publication here, the third one, which has to do, is mainly about innovation in algorithms, where we were using OpenMP. In fact, the fourth paper also, computational physics, communication. These two papers were about algorithm progress. But we continue to analyze the data and say that the Blue Waters project has at least something like a year to live on, right? So at least we're not going to stop. So the question of accuracy is very important. Sometimes I would say that people have been overlooking it. We all get so excited about generating the highest Reynolds number, doing the largest simulation possible. Well, what about accuracy? Are we doing the most accurate simulation? Sometimes I say the answer may not be so comfortable. Let's say. So we all know about the importance of resolution in space, resolution in time. We're talking about partial differential equations, and the Navier-Stokes equation. We have aliasing errors because we want to use pseudo-spectral methods. They're non-linear terms that give us something else. And we all have to make sure that we have statistical accuracy. In the last simulation, for example, do we have enough particle pairs? That's one of the questions that we have to answer. And can the simulation at a high resolution resolve any doubt? Even 92 cube is not enough. Let's do 16K cube. 16K cube not enough. Dreaming ahead, 32K cube sometime in the future. Will that solve all our problems? It may not, unfortunately. We have to, on the other hand, to say, given a certain simulation, we always recognize that some results are more accurate than the others. And so it depends. What are we looking for? And now, we sample the resolution 8 times as many grid points, and in fact also twice as many time steps. The cost of 16 is quite expensive. Can we do that? If we do that, it will be relatively short. Fortunately, the small scales that we are after in my work, they have short time scales. If you want to study things that change quickly, maybe we don't have to simulate that long. That is what might actually be saving us. And the spatial resolution here, so those of you who are in field turbulence will know all of this. But I would say that if we want to study the small scales, then we have to have better resolution, and that is quite difficult, especially high Reynolds number. And of course, what we can do always is we find the grid one again at the same Reynolds number, see if things change or not. Probably certain things will change, but then the other question is, given a set of data, how do we know what aspects of the data that we have are actually accurate? So we can take a relatively well-resolved velocity field, we can truncate it, filter off some of the high wave number content, compute the statistics again. Have they changed a lot? If they have not changed a lot, that means that the simulation certainly is accurate enough. Otherwise, we have something to worry about, and this is the post-processing task. Doesn't require us to go to the next highest level. On the other hand, the limitation is that we don't know what the Navier-Stokes equation is going to do with it, and this is not really allowing us to obtain some more accurate answers. So typical resolution in partial differential equation, this is so-called Coulomb number. And this is a three-dimensional definition. We can take, for our practical purposes, something like 12 times RMS velocity delta t divided by delta x, assuming that we're operating on the cubic domain. And what about the time step divided by the so-called Kolmogorov time scale, the function of the Coulomb number, function of the grid spacing, function of the Reynolds number. This is an expression here which seems to be satisfied quite well by our DNS data. Often we find that delta t is very small compared to Kolmogorov time scale, less than 1%. So we made a mistake earlier. I think we didn't worry about this enough. It turns out that though delta t seems to be so small by this criterion, that is not really sufficient. And I'm going to show results over a range of Coulomb numbers. We start from 0.6 and then we drop it by a factor of 2 and another factor of 2. But before we go there, let's, I think, very briefly, I think this is dissipation and entropy. I think these two quantities appear in the previous talk, just slightly different symbols, I think. And I'm going to skip this, but these are both of these are very important parameters of the small scale turbulence. And we're looking at the PDF. Enstrophy generally more intermittent. Those lines in blue are entropy. What it might mean by intermittency here, there's a greater tendency for extreme values. Say here we're talking about 4,000 times the mean value. Okay, so imagine that's almost like the end of the world, with some place in the world, 1 year gets 4,000 times the average rainfall. That place probably would not exist anymore. And we have now what are these lines here are the arrows. These are essentially the filter that I'm talking about. We drop off the high wave number parts of the signal, then these PDFs change substantially. So there's one, and also another indication of the problem that we have actually is this is on a log scale on the right hand side. You have a line, you have a straight line here near the tails that implies that the moments do not exist up beyond a certain order. Then that's it regarded as not physical. So resolution in time here. I apologize if there's too much detail on these slides. So let's say that at a relatively low resolution, and in fact for all three resolutions in space, if we have the red line is for the Coulomb number 0.6, if we drop the Coulomb number and then another half of it and so forth, then you get lines in green and blue. Green and blue are almost coincident, but the main thing is that there's a big difference between the red and the other two. So that shows that resolution in time actually has been a problem. And what about resolution in space? Don't we expect if we find a grid spacing, we're able to capture larger spatial gradients? Well, in order to see that, we have to have a Coulomb number that is sufficiently low. Coulomb number 0.6, those three lines, green and blue, they all seem to be jumping around each other. That should not be the case. Physically, we know, but we have to have a sufficiently low Coulomb number. And then, so we learned the lesson of some of the numerical errors, but then is everything lost? Maybe not. First, we can, with our more accurate results, we can try to compare the effects of different resolutions. Again, now we see a little bit of a kind of conversion. If you have spacing, do the result change anymore? Here, well, they coincide to a large degree. Of course, in a higher resolution, you are expected to capture some samples which are even larger. And then we can compare the PDFs of the dissipation and entropy again, and red and blue respectively. They are not the same. They don't coincide at the tails at the far values here. In particular, we find that they have a sort of a different a similarity in shape. In fact, both of them are well captured by a structural exponential formation. We find very good fits if we keep those exponents inside the same, but we're changing this factor B epsilon or B omega. We also find that double the then the PDF is actually that green dashed line is actually quite close to
to the PDF of the Enstrophy. So there's something that we'll have to go deeper into multifactor theory in order to have a better explanation. Okay, coming back to our, the highest Reynolds number work that we did on blue waters. We published a paper in Proceedings of National Academy of Sciences. So we claim that red and blue are coinciding at the extreme values. On the face of it, the evidence looked convincing, but then you know a little better. One of my former student who is still involved in this project, he made use of the 95% holiday. In case you did not notice that at the end of 2017 and the first few days in January, we took advantage of the 95% discount. We were able to do something that we were not otherwise going to be able to afford to do. So we did that simulation, 12K cube, a lower Coulomb number, to better resolve in space, better resolve in found these two curves are exactly the same, essentially the same scales on the left. So at least we have some better results. But what about that? Well, I said all is not lost, though. Does it mean that the old data we should cast aside? Not quite, right? Because if you want to, we were looking at the less extreme values, if we are averaging over some certain regions of space, then that averaging actually helps us, holds down all the some of the uncertainties. Okay, thank you. And so I have a few slides to go, and let's not, well, say local averaging is averaging over a volume of space. Whenever averaging in statistics, all the disorder goes down a bit. Then that's what is helping us. And so we have something like 8192 cube, 16K cube, and a 16K cube filter, and the story about plots is that all of them look quite flat over the same region, same range of the scale separation out. More recently, we have tried to work on another thing about circulation. What is circulation? Circulation is mathematically defined as a linear around a certain contour or the of the vorticity. People in aerodynamics know about this a lot, because you don't have a circulation around the airplane, around the wing surface, the airplane is not going to fly at all. Yeah, circulation is what allows now the airplane to take off. And so what about in the spatial, in the case of a turbulence, of a turbulent flow, the spatial structure of the vorticity field will have some importance, obviously. But how much of circulation is not so much, because one of the things that students complain to me when I talk about circulation is that, how do you measure it? Well, I said, there's no way to measure it, because you have to define, on top of the vorticity, you have to have a signal. I'm sorry, you define a certain, you cannot measure it directly. In terms of theories, there is a suspicion that maybe the shape of the closed path that matters so much. If you take a square or circle, a rectangle, as long as they have the same area, certain things seem to be quite similar. And our results show that so these numerical errors are not disrupting the story very much. And concluding remarks, this is a cover of a book, A Voyage to Turbulence. Think about these people in these boats, fearing for their lives. That's what we don't have to, of course. On a computer, there are no safety constraints. So we can produce a visualization, which was done by my student Science Strike a number of years ago. So I think that there are exciting stories. Well, there are some eventful moments like these. Worry about bugs, of course. How long is my job going to waste? And will it fail? These things. Everybody on our machine, we have to confront questions like that. But we expect to have more publications going in the next few months. Anyway, so let me come to some remarks about NSF cyber infrastructure. I was at the workshop at NSF last week, and I think we would all agree that NSF investments in Blue Waters and other machines like those at Texas and other centers have a major impact. And for example, the meaning of massive parallelism changed over time. 20 years ago, 64 was considered massive. Now maybe 64,000 something. And there are massive data sets to deal with. That's it, of course. That is the result of having the computer time. As we look towards the next group, wherever it might be, whatever architecture it is, I was saying that all of us in the community have to be willing to accept, have to be willing to take some risk. And of course, that's how many of us have gotten to this point in the first place. I'll say that the need for computational resources really no boundaries. Okay, fluid dynamics, solid mechanics, everything. I'm not saying that we should put all the money, all the funding into turbulence. And I would think personally we need greater support for maintaining the data. How do we maintain the software? And also we have to be able to take some risks. For example, if someone would say this would be a good way to rewrite your program, and you've spent a year of your life on this. It turns out that, well, helps by 10%, then was it worthwhile? Sometimes we do have questions like that, but then we cannot afford not to try, depending on the